Let us start our lecture today on soil dynamics. We are continuing with our module 3 on wave propagation. So, a quick recap what we have studied in the previous lecture. We have seen how to formulate the equation of motion for 3-dimensional wave propagation, and these are the basic 3-dimensional equation of motion for a 3D elastic solid in x direction, y direction and z direction. Then we have just brush up our memories on common expressions for various modulus in terms of two Lami's constant, that is lambda and mu. So, how Young's modulus, bulk modulus, shear modulus and Poisson's ratio, these are expressed in terms of these two Lami's constant, we have seen that. Then to obtain the solution for the 3D equation of motion, what we had obtained in the first slide today I have shown. So, the same thing for the first type of wave, we have obtained what is the wave equation, and in that we have expressed the primary wave velocity V p in terms of two Lami's constant and density of the media like this, and in terms of shear modulus and Poisson's ratio and density of the material, the V p is expressed by this expression. Then for the second type of wave equation, we have seen this is the form of the equation, and the secondary wave or S wave is expressed in terms of Lami's constant like this, which if we express in terms of shear modulus, it comes out to be root over g by rho. And comparing the expression for velocities of primary and secondary wave, we obtain the ratio of primary velocity to secondary wave velocity is just a function of Poisson's ratio of the material and expressed by this expression. Then we have seen waves in semi-infinite body, that is very close to the ground surface, and with depth it is decreasing drastically. We call that as Rayleigh wave. It moves in x direction, and with increase in depth z, it decreases drastically as I said, but there is no variation in the other direction of y. And the relationship of that Rayleigh wave, how to compute the Rayleigh wave with respect to the shear wave, we have seen this is the equation we have to solve, and the relationship between the P wave, S wave and Rayleigh wave with respect to S wave for different values of Poisson's ratio, how it varies was shown. Then another type of surface wave we have considered, the love wave. The condition to generate the love wave was the superficial layer must be very much softer than the layer below it. So, that is why G 1 by rho 1 should be much lower than G 2 by rho 2, that is the condition to generate love wave. And the love wave also we have expressed in terms of shear wave velocity, and this is the expression by solving which we can obtain the expression for love wave velocity from the shear wave velocity of the two corresponding medium, and how it varies with respect to frequency, that also we have seen. After that, we had studied waves traveling in layered media, that is when waves are moving from one media to the another media at the interface, when it is hitting the incident wave, a component of it is getting transmitted in the next media, that we call transmitted wave, and another portion is getting reflected back to the same media, we call that as reflected wave. And to maintain the compatibility, we have seen that displacement compatibility as well as stress compatibility has to be maintained at the boundary. Boundary means at this junction between the two media, where we have considered x as 0 as per our chosen coordinate system. So, that is why x 0 u incident wave and reflected wave, summation of that should be equal to the transmitted wave. And similarly, for the stress amplitude, we have seen that incident wave stress amplitude plus reflected wave stress amplitude must be equal to the transmitted wave stress amplitude. Then we have defined one parameter known as impedance ratio, which is nothing but the ratio of the multiplication of density and shear wave velocity of one media to the other media. One media means when waves are traveling from medium 1 to medium 2, then impedance ratio is expressed in this way. Then effect of impedance ratio on various displacement and stress amplitude. We have seen how the displacement amplitude is getting amplified when impedance ratio is less than 1, and which is of our concern, because in soil generally waves, when it is traveling from a very lower strata, which is typically very hard in nature, to a softer media on the top surface, then there is a chance of getting the incident displacement amplitude magnified by several times when it is coming to the higher media or top media in form of transmitted wave displacement amplitude. So, that we had seen, and it is of our concern as a designer. Now, coming to the nature of the waves we considered in our geotechnical engineering problems or soil dynamics problems. Suppose we have an elastic half space. So, semi infinite body we are considering ground surface. This is the ground surface we are taking it, and say we have several layers below it, which is quite typical and quite obvious, and the shear wave velocity, say in this layer Vs1, in this layer Vs2, in this layer Vs3, in this layer Vs4, in this layer Vs5, and so on, in such a way that typically this Vs1 is much less than Vs2, is much less than Vs3, then this is much less than Vs4, this is less than Vs5. What does it mean? This is stiffer layer compared to this one, then this is stiffer layer compared to this one, this is stiffer layer compared to this one, and this is stiffer layer compared to this one. So, as we are approaching towards the ground surface, the soil condition is becoming softer and softer. So, typically we are considering like this. Now, what we have seen in the previous lecture, that in case of 3D inclined wave, when waves are traveling, they must follow the conventional Snell's law, that is sin I is the angle of incidence with respect to the vertical, v is the velocity of the wave in that particular media, that has to be maintained constant. And when there is an inclined wave is hitting any interface between two material 1 and 2 like this, incident P wave can generate reflected P and reflected SV wave and transmitted SV and transmitted P wave in the another material. When incident wave is SV type, then some portion get reflected as P wave and SV wave in the same material, and some gets refracted or transmitted in the other material as SV or P wave. And when it is incident SH wave, in that case we have seen that the reflected wave in the same material as SH wave and the refracted or transmitted wave as SH wave in the other media. If you look at it, this is our angle of incidence. Okay. This angle with respect to vertical with which the incident wave is hitting the junction. So, this is our angle of incidence and this is the velocity. When it is getting transmitted or refracted in the next media, if this is a softer media, this is our angle of I. To maintain that ratio constant, sin I by V remains constant as per the Snell's law. So, what happens? Let us look at here. Suppose any wave traveling here, whether it is SV or S wave, we are considering any Vs wave, it is hitting from this layer in this direction, some inclined wave. So, when it travels to the next media, that is when some of it gets transmitted, being this layer as a softer layer than this fifth layer, what will happen? It will slightly come like this. So, the angle of inclination with respect to vertical will decrease. Further, when it hits the next media, as the layer 3 is softer than layer 4, further it will come like this. Again, when it hits the boundary of layer 2 and 3, as the layer 2 is softer than layer 3, again it will come like this. And when it hits the last boundary, that is layer 1 to layer 2, as the layer 1 we have considered as softer than layer 2. So, when actually we are getting in the range of our geotechnical investigations or the geotechnical design aspects, what you can see, the Vs wave which we should consider in our design is basically almost vertical. Okay? So, that is why in many of our design problem, we hardly take any inclined nature of the waves. We generally take whether it is shear wave or primary wave when we are considering near ground problems. In that case, we mostly consider it is as vertical. So, vertically propagating wave Vs or Vp when we consider the design. Okay. Is this clear why in our design there is hardly we consider any inclination of the waves? This is the basic reason, because it has to travel several layers and typically it has to travel from a harder layer to a softer layer. So, in the previous lecture, what else we have seen? We have seen what are the earthquake waves and how it gets generated, release of energy, and how they got recorded through seismograph, and seismogram is the graph, and how we have classified the earthquake or seismic waves basically in two categories, body wave and surface wave. Again, subclassification of body wave is in P wave and S wave, and surface wave subclassified in two Rayleigh wave and Love wave. So, this is the wave, the measurement of the earthquake waves are done, and different depths of earthquake we have studied: shallow depth earthquake, intermediate depth earthquake and deep earthquake. And we have seen that most of our earthquake in history is recorded as shallow depth earthquake. Then we talked about different layers of the earth which we have learnt in our earlier geology course in undergraduate. It composed of crust, then mantle and then core. So, crust is also can be continental crust and oceanic crust, mantle can be upper mantle and lower mantle, and core can be outer core and then inner core. Then two types of seismic waves what we have mentioned just now: body waves transmit energy through the earth's interior, that is primary wave and secondary wave gets generated, and surface wave they transmit energy along the earth's surface. So, this is the basic nature of the primary wave. When it travels through a media, we have seen how when earthquake focus is there, waves is traveling in this direction, this is the direction of P wave propagation. The sequential contraction and expansion of the media is going to take place. So, that is why it is called compressional wave also, primary wave or P wave. What are the other characteristics we have seen for P wave in the previous lecture? That their typical crustal velocity is about 6 km per second, and it travels through all the media, that is solid, liquid or gaseous, and material movement is in the same direction as of the wave movement. And its behavior is it causes dilation and contraction of the earth material through which it travels. And about their arrival, they arrive first on the seismogram because of their very high crustal velocity. That is the maximum crustal velocity among all the waves. So, P wave is having maximum crustal velocity among the 4 types of waves. And we have seen from this picture in the previous lecture that though suppose the focus of earthquake or epicenter of earthquake is somewhere here, then waves keeps on traveling to everywhere, and that is why when any earthquake happens, we say that gets recorded in all over the world wherever the seismograms are located, and it can record. But saying that, we have seen that waves are traveling here. So, all the stations with seismogram at these places can record this earthquake, also these places. But we have seen there is a particular zone, and that zone dimension is 103 degree to 143 degree approximately, that is called P wave shadow zone. What is the meaning? We have seen that because of the boundary reflection and refraction of this P wave from this mantle to core, outer core, some portion of P wave cannot arrive in a particular region, and that region is within this angle, that is called P wave shadow zone. What does it mean? If there is any seismogram located at these stations, at these locations, in that case this seismogram cannot record any earthquake wave getting generated because of earthquake at this place. Fine? Okay. So, these are all about P waves or primary wave. Now, let us start or continues with the same thing for our today's lecture with next type of wave, that is secondary wave. So, what is the basic behavior of secondary wave? Suppose earthquake focus is here and direction of S wave propagation or secondary wave propagation in this direction, then its behavior is something like, if you use a rope and then it continues vibrating like this. So, it is vibrating in this direction and this direction, this direction and this direction. So, this is the direction of motion of the particles. So, that is why we said whenever S wave travels through a media, if the direction of wave propagation is in this direction, the particle movement is almost orthogonal to the direction of wave propagation. So, that is why the movement of the particle are like this. So, this way we can explain how the propagation of S wave continues in a particular media. Now, coming to the typical characteristics of secondary wave, S wave or secondary wave is having typical crustal velocity of about 3 km per second, which is just half of the primary wave velocity. So, primary wave velocity is having crustal velocity of about 6 km per second, it is having 3 km per second. What is the behavior of S wave when it travels through a media? It causes shearing and stretching of the earth material through which they pass, generally cause the most severe shaking and very damaging to structures. And another important characteristics of secondary or shear wave or S wave is that it can travel through only solid media. So, this is very important to note down, because we know water or air they cannot take shear. So, that is why there is no question of arising that shear wave can travel through liquid or gaseous media. It can travel only through the solid media. Okay? Now, shear waves move material perpendicular to the wave movement, just now I have mentioned that. And what is the arrival time of the secondary wave in a seismogram? It is the second wave which arrives to the seismogram. So, when an earthquake occurs, seismograms are recording different waves. First arrival is for P wave because of its very high crustal velocity. Next higher velocity is for the S wave. So, next second arrival is the S wave in the seismogram. Now, let us look at this picture. Again we are considering, say this is the location on the earth where the earthquake is getting generated. So, this is a kind of epicenter or focus of earthquake, and from there energy gets released. So, different waves are getting generated and traveling through this media. So, we are now talking about only the say S waves. So, these are the S waves traveling. What happens when on the other parts of the earth, that is at these places, if we have these seismograms are located stationed, they can record this S wave, right. But look at this zone, that is from that 103 degree from one side to the another side 103 degree. This zone no shear wave comes because of the earthquake getting generated at this point. So, it is called S wave shadow zone. Shadow zone means no waves reaches at those places. So, if we have some seismograms located at this part of the earth, they cannot record any S wave getting generated due to the earthquake at this location. Why it is so? Because see, S wave travelling through this mantle is fine, because mantle is mostly the solid material of the earth. When it travels in this direction and hits the boundary of mantle and the outer core. What is the outer core? I have explained, it is basically a liquid, molten liquid, right? It is a fluid state. So, obviously, the shear wave cannot travel through the liquid media, it travels only through solid media. That is the reason why it is just dead stop at this boundary. Nothing will get transmitted in the next layer. That is the reason why on this side we do not have any S wave coming out, because of the earthquake energy getting released here. So, hence this is our S wave shadow zone, it is called, and it is mentioned S wave velocity drops to 0 at core mantle boundary. So, this is the core mantle boundary, which is known as Gutenberg discontinuity. This boundary of mantle to outer core is called Gutenberg discontinuity. So, what I have explained just now, the combination of P wave and S wave, now I am showing through this slide. P wave is shown in black color arrows and S wave is shown in red color arrows. Suppose earthquake epicenter is somewhere here, earthquake energy gets released here and then waves are travelling throughout the earth interior, and other parts of the earth are also getting recorded these values. So, P waves you can notice at this boundary of mantle to outer core. So, P waves can get transmitted to the liquid media, whereas shear waves cannot get transmitted in the liquid media. So, they stop here itself, whereas P waves get transmitted, that is refracted, then again from this boundary it gets refracted and comes here. So, this is the zone about 103 or 105 degree to 143 or 140 degree is shadow zone for P wave, and this entire zone is shadow zone for S wave. What does it mean? If we have any seismograms located at these places of the earth, at these locations of the earth, they can record in their seismic station, they will record both P wave as well as S wave, because both the waves are coming to those locations, right. And in the seismograph, what they are getting finally, it will look like this with respect to time, because as I have mentioned, P wave is having very higher crustal velocity. So, they will arrive fast in the seismogram. There will be a time lapse in between the arrival of P wave and S wave, then second one will come the S wave, because it takes time, because of its velocity, crustal velocity is half of the P wave velocity. So, it takes time and then S wave comes to your seismogram, and then the record of seismograph will look like something like this. Whereas, if some seismic recording stations are located at this zone, that is between about 105 to 140 degree this region, their seismogram will record nothing, because neither P wave nor S wave are reaching within this zone, because it is a shadow zone for both P wave as well as S wave. So, that is why though the seismic station is there, recording station is there, but they cannot record anything. They will not feel anything as if any earthquake has happened to the other part of the world. Whereas, if some seismic stations, recording stations are located at this zone, it will record only the P wave. Also, it is a shadow zone for S wave. So, no S wave will be getting recorded, they will record only the P wave in their seismogram. So, this clearly shows how worldwide the record of P wave and S wave can take place for an earthquake occurring at a particular place. Okay? So, once again, this is inner core, outer core, this outer core is liquid state, this is mantle and this is very shallow crustal depth. This boundary is called Mohorovicic discontinuity, that is the boundary between crust and mantle is known as Mohorovicic or M discontinuity, and the boundary between mantle and outer core, this boundary is called Gutenberg discontinuity or G discontinuity. Okay? So, how the P wave and S wave they vary, the velocity they vary as we go from crust to the inner core in terms of distance. So, this x axis shows us distance in kilometer. This first graph shows velocity about kilometer per second. If you look at here, the P wave is about, as I said, crustal velocity is 6 kilometer per second. So, as it goes deeper, the media is stiffer or heavier. So, its velocity gets increased here. When it comes to this boundary, that is Gutenberg discontinuity, there it drops and now it is a liquid or molten fluid state. So, velocity will obviously be much lesser than what it is in the solid state. So, it drastically comes down. Then also with increase in the depth towards the earth's center, it keeps on increasing. Again at this boundary or interface there is a jump and then it continues in the inner core. That is the distribution of P wave velocity across the earth's interior. And what about S wave? Its velocity, crustal velocity is about 3 kilometer per second. When it goes deeper in the mantle, it increases, but when it comes to the boundary of mantle to outer core, it drops down to absolute 0, because this outer core is liquid state. And how the earth's interior density varies? So, as I was saying that from crust to mantle, the density keep on increasing. So, this is the typical values of density in gram per centimeter cube from the earth's crust to mantle and then outer core and inner core. Coming to the surface waves, so they travel obviously within the crust and not only within crust, very close to the ground surface. So, that is why the name surface wave. If you look at this is the earthquake focus, S wave, P wave, they are traveling inside also and getting recorded in the other side, whereas surface wave they travel surfacially as the name suggests only in this direction to a particular certain distance. So, they travel just below or along the ground surface, that is the condition for surface waves. And the wave velocity they are much slower than the body waves. So, velocity of these surface waves are much lower than P wave and S wave. And what are the effects of them? They cause rolling and side to side movement of the particle. That is, when the surface wave travels, the particles either they roll or side to side movement occurs, and these are specially damaging to the buildings constructed on the ground surface. So, this is the two types of surface waves. You can look here. Here side to side motion occurs when the direction of surface wave propagation is in this way. The particle moves in this direction as well as this side to side movement occurs. So, side to side swaying of objects on earth's surface is opposite to the wave motion. So, these are suppose some buildings or some structures constructed on the ground surface, they can have side to side motion because of wave propagation like this. And another type of earthquake wave, they can cause up and down rolling type of motion like this. So, the direction of surface wave propagation in this direction, however, the nature is creating on the ground surface something like rolling type up and down motion. What does it mean? It is will give you a feeling as if you are traveling in a sea in a boat. So, as the waves comes, that kind of rolling motion is getting experienced, and any structure constructed on the ground surface, they can roll and also upside down things can occur. So, this is the nature of destruction caused by the two types of surface waves. So, coming to the sub-classification of surface wave, what we have seen, Rayleigh wave, their typical velocity is about 0.9 times of shear wave, that we have seen through the expressions of relation between Rayleigh wave and shear wave, that is a function of only the Poisson's ratio, right. In the previous day's lecture, I have mentioned that, and today also in recap I have mentioned. So, we have seen Rayleigh wave velocity is about 90% of the shear wave velocity. Its behavior is they cause vertical together with back and forth horizontal motion. So, motion is similar to that of being in a boat in ocean when a swell moves past. And the arrival of Rayleigh wave in a seismogram, they usually arrive last on the seismogram. What does it mean? The Rayleigh wave velocity is having least velocity among the 4 categories of the waves what we are studying. So, that is why they arrive last on the seismogram. And the nature just now we have seen this kind of rolling upside down movement can occur when the wave propagates in this direction and structure can destroy in this way. So, that is why it is said Rayleigh wave is the most damaging one for the structures constructed on the ground, not only because of its behavior of motion of the particle due to the wave propagation, but also as I have mentioned, it takes about 2/3 of the energy getting generated in the earthquake getting released in the form of Rayleigh wave finally. And about love wave, its typical velocity depends on the earth structure, but obviously it is less than the velocity of S wave. So, the relationship between love wave and S wave also we have seen in the previous lecture, the equation how to obtain the love wave velocity. And its behavior, it causes shearing motion horizontal similar to the S wave, that is when wave propagates in this direction, it moves in this direction similar to the S wave, and their arrival is usually arrive after S wave, because its velocity is less than shear wave. So, obviously, it arrives in the seismogram as the third one. So, first one in the seismogram is P wave, second one is S wave, third one is love wave, and last one is Rayleigh wave. In the order they appear in the seismogram, but obviously they appear before the Rayleigh wave. So, you can see depending on the velocity of shear wave, love wave and Rayleigh wave velocity, their recording time and the time difference between recording of shear, love and Rayleigh wave in seismogram is hardly any difference is there. They almost come one after another. So, S wave soon after that love wave, soon after that Rayleigh wave. That way it getting recorded in the seismogram, whereas there is a substantial amount of difference between the P wave and S wave arriving at the seismogram. So, how to make use of that to locate an epicenter of an earthquake? Because when an earthquake occurs, suppose in that place we do not have any seismographical recording station. Does that mean that we cannot record the intensity of earthquake or location of epicenter at that place? No. Then what is the use of having so many seismological stations around the world? From their recordings, it is possible to identify the exact location of the earthquake epicenter. How? Let us see. So, this is once again what we have talked about, just various earthquake waves. You can see fault rupture at that point, focus point, this is earthquake focus, and if you take a vertically upward line which is hitting on the ground surface, that on the ground surface that point is called epicenter. So, focus is where actually it is getting generated, earthquake focus, and earthquake epicenter is on the ground surface, vertical projection of that point to the ground surface. And then body waves travels through the media, whereas on the surface only the surface wave travels, and this is the typical behavior. And nature of different waves we have seen. Nature of P wave is continuous extension and compression, that is push and pull kind of nature in the media when the direction of energy transmitted in this direction, and nature of S waves is side to side movement up and down. Nature of Rayleigh wave is sideways in horizontal plane, and whereas nature of Love wave is sideways in the horizontal plane, and nature of Rayleigh wave is elliptic vertical plane. So, in this way rotating or rolling ups and down can occur. Now, locating an earthquake's epicenter using the seismological recording stations data, that is our seismograph data, how to locate an earthquake's epicenter. Seismic wave behavior is we have studied just now. P wave arrives first, next is S wave, next L and R wave, Love wave and Rayleigh wave. So, after an earthquake, the difference in arrival times at seismograph station can be used to calculate the distance from the seismograph to the epicenter. So, with respect to time, on the plot, that is when seismogram are recording on that drum and that graph sheet, how they will record, the typical record of a seismograph will look like this. Initially, when there is no earthquake, initially it will keep on vibrating like this. It is actually a background noise. So, you can neglect those things. When actual earthquake occurs at any point around the world, if it is not within a shadow zone of that particular wave, then obviously some undulations and wave will arrive, and that is the arrival time of the P wave. Then it will slowly die down, and after some time you will notice then another large magnitude wave is getting recorded in your seismogram. That is nothing but arrival of S wave, arrival time of S wave, this is arrival time of P wave. So, as I was mentioning, there is substantial difference between the time of P wave arrival and S wave arrival in a seismogram, provided there is one condition. Remember, the station should not be located at a shadow zone of any of these two waves. Otherwise, if it is located in a shadow zone of S wave only, obviously these waves will not come, only you will record this P wave. And if it is located in the shadow zone of P and S wave both, nothing will appear. So, you will not feel even that some earthquake has occurred at some part of the world. But obviously, we are getting several areas of the earth which are not in the shadow zone of any of the P wave or S wave, that is between from that 0 degree, if we consider at the top point where earthquake is occurring, on both the sides about 103 or 105 degree. So, within those region, whatever seismological stations are located, they can record both P wave and S wave. So, their arrival time we can get from the stations or this seismograph, and then of course, the Love wave and Rayleigh wave, they keep on continuing coming and getting recorded. So, we are concentrating on this aspect, that is the time difference between P wave and S wave. So, how we can make use of this? It is called by using S minus P time formula we can locate the distance of an epicenter. How? Because we know time is nothing but distance by velocity. So, the time for shear wave or S wave recorded is nothing but the distance it has travelled from the earthquake epicenter to the recording station. D is the distance between the epicenter to earthquake recording station by V s, and the time for P wave or primary wave is, it has also travelled the same distance, but for V p. Okay. So, T s minus T p, because in our recording station the value of T s will be larger, right, because it is on later time, T p will be lower than T s. So, T s minus T p is nothing but d by V s minus d by V p, which is nothing but d times V p minus V s by V p V s. Therefore, d is given as V p minus V s by, therefore, d distance can be computed as V p V s by V p minus V s times T s minus T p. Okay. So, this is the simple expression. We can find out the distance of an epicenter from a seismological recording station. So, any station which is recording both P wave and S wave, knowing the crustal P wave velocity and shear wave velocity, which already I have mentioned their typical values, and the recording time of S wave and P wave, very easily we can compute the distance between the epicenter of earthquake and the seismological recording station. Now, how we can make use of this to locate the epicenter? Because at one station on the earth surface, it has recorded the waves travelled because of earthquake to that station. Suppose this is our seismological recording station at this point. T s T p we have recorded, V s V p value typical we know, we obtain the value of d. Now, where is that earthquake epicenter? D from this direction d, or in this direction d, or in this direction d? Where? We do not know. So, it can be at any distance d with a, if we draw a circle taking that seismological recording station as the center on a graph paper, with a radius d, if we draw a circle, within that periphery any point can be the possible location of an epicenter. Now, how to locate an exact location? Let us see. So, let us look at here what I have mentioned just now, the same thing is written. If average speed for all these waves are known, then S minus P time formula is used to compute the distance between a recording station and an event, means where the earthquake occurs. And this is the expression, very simple way we can obtain this expression. Now, before coming to this, let me mention this method. It is called 3 circle method. What is 3 circle method? Read S minus T times from minimum 3 seismograms, that is from 3 seismic stations, wherever you have recorded both P wave and S wave, you get the value of this S minus P time. Then compute the distance of each of the event from that recording station using that S minus P formula, which we have studied just now. So, for example, suppose This is our station 1, recording station 1. So, from this point at a distance of d1, suppose we got the distance where then earthquake has occurred. So, event has occurred at a distance of d1. So, let us draw a circle taking that point as a center, recording point as a center with radius as d1. Let us draw a circle. Similarly, for another recording station which also have recorded the same earthquake, with both P wave and S wave arrived to their seismograph. So, the seismogram record will give us the S minus P formula, from which we can calculate the distance from that recording station to where the earthquake has occurred. In a similar way, another circle with a radius d2. Fine. Similarly, suppose another station, another recording station, this one has also recorded both P wave and S wave, and using the same S minus P travel formula, travel time formula, we can obtain another distance, say d3, where the earthquake has occurred. So, let us draw another circle taking this as center and d3 as radius. So, where actually the earthquake has occurred, where these 3 circles will meet, this is the point. Look at here, I am pointing here with this pointer. So, this is the point where these 3 circles meet, that is the actual location where an earthquake has occurred. So, this is the location of earthquake epicenter. Clear? So, in using this 3 circle method to obtain the earthquake epicenter, one basic assumption is the earthquake is relatively shallow earthquake. Okay. So, epicenter is relatively close to the hypocenter, and overlapping of the point gives us the event location. And many a times it will happen, you may see that we may not get an exact overlap at a particular point, but we will fairly get a good idea the common zone, interface zone of these 3 circles, very small common zone. If it boils down to a point, then obviously we got the exact location. If not, at least we get some idea of where the earthquake has occurred. So, this is the way how worldwide seismic recording stations are used to obtain or to locate the epicenter of an earthquake. This is the way we use. So, this 3 circle method is mentioned here. You can imagine if we use more number of circles here, obviously we will get much more precise result, because suppose some recording station is having some difficulty during the recording process, or some manual error, or some damage to the instruments, or something else has happened. So, instead of relying on only those 3, you can use say 6, 7, 8, any number of recording stations and plot that in a graph sheet or paper like this, draw a circle like this. So, most of them where they will converge to a single point, or at least to a single shadow zone, common zone, that will give us the location of earthquake epicenter. This is how worldwide till date the earthquake epicenter is obtained, because many a times what happens, earthquake can occur at any place within a seabed. So, there is no recording station. Within a desert, there may not be any recording station. So, how we locate the earthquake epicenter? This is the way, because the waves travels, and P wave and S wave, they have substantial amount of difference in their velocity, and that is why in their arrival time. So, that is how we can compute their location of earthquake epicenter in this way. Now, coming to another method, this is seismic travel time curve. This method is called seismic travel time curve. Concept is almost similar. What it does, measure the time between P wave and S wave reaching on the seismogram, what we have done just now. use the travel time graph to obtain the epicenter in this manner. So, if the speeds of the seismic waves are not known, then this travel time curve for that region to get the distance is very useful. The 3 circle method and the distance what I have explained and wrote the formula, that we can use provided we know the typical crustal velocity of P wave and S wave very accurately. If it is not exact, then we may get a erroneous data. So, that is why I said instead of relying on 3 circle, let us use as many number of circles as possible based on available recording stations. But suppose if we want to get rid of that error where we do not know the exact values of V p and V s, the crustal velocities, this travel time curve method can be used. So, let us look at here how it is done. Suppose one seismogram A, another seismogram B, another seismogram C at 3 different locations, all of them are recording both P wave and S wave. And for seismogram A, the recording, so this is our time axis, you must have understood, okay. And this is the arrival time of P wave, then after some time S wave start arriving in seismogram A. So, this is the time interval. For example, it is given, let us say 3-minute interval between the arrival time of P wave and S wave for seismogram A located at one point. In another station, seismogram B, the arrival time of P wave is somewhere here and arrival time of S wave is somewhere here, and there is a time difference of about 8 minutes say. And another point of seismogram recording station, let us say it is C, where P waves arrives here and S wave arrives here, and there is a time difference between their arrival time is say about 11 minutes. Now, knowing these 3 time difference of 3 locations and what you know, this is known distance from seismogram location A to B, B to C. Okay. The recording station distance obviously is known to us. What we can do? We can take a graph paper. Now, distance travelled from earthquake epicenter in the x axis and this y axis shows time elapsed after the start of earthquake. Now, we try to match these 3 locations in such a way in the graph sheet that their distance as well as individual distances between the stations and the time intervals, they follow a continuous pattern. Okay? That can be easily done by changing the locations of the positions of those seismogram and their distances. If you slide them over the paper, what you will get? At which location they follow a continuous pattern of movement of this from time elapsed after starting of earthquake to distance of earthquake epicenter. And obviously, the smaller time will be very close to the epicenter, smaller time interval between P and S wave, then the intermediate one and then the higher one will be obviously farthest from the epicenter. So, that way you can get a fair estimate of the distance of earthquake epicenter from those stations in this manner. So, this is called seismic travel time curve method. Okay. So, with this we have come to the end of our module 3, that is on wave propagation. We will stop here today.